Welcome everyone. I'm going to go through this session together with you, and my intention is, as David said, to update you with our machining monitoring development at Kistler. So let's go. I will start talking about a little bit, introduce the subject, what it means for us at Kistler about machining monitoring. Is a quite a big topic, and then give some examples of the cases where we can share with you, and then at the end I will make a short summary, and we will see if we can manage to get also some questions from you. As David said, the session is recorded, so it will be shared with this with you. If you'd like to get the recording, please feel free to contact David afterwards. Let me start with explaining a little bit how Kistler strategy is built. As you know, Kistler has been market leader when it comes to metal cutting research, development, measurement technologies, right? So many of our products, stationary dynamometers, rotary dynamometers, our electronics, our software DynaWare has been used quite many years now in research and development of the machining processes at universities and in industrial R&D centers and so on. But now we are moving more and more into machining monitoring. And of course, when you move to machining monitoring, we are utilizing the already existing sensors and electronics and even softwares that Kistler has been using in process monitoring in other applications, right? And one of our biggest motto is, of course, flexibility and simplicity. So that means that we really move from high-end products to simple and flexible solutions to install and integrate in the machines with already existing products as a start. If you look to production monitoring, of course, the focus it's on key performance indicators, right? And that is time, cost, quality, and that includes also traceability, delivery, environmental impact, and that is the core KPI values that have been also used in especially lean manufacturing by many of you if you are also producing parts with machining. Often when it comes to production optimization with focus of those KPI performance indicators, we are not talking about absolute measurement technologies. In some cases, even relative force measurements are sufficient, because you really would like to see the change between a normal state of the process or machine and the abnormal state, right? So it can be relative. We are working with machining, so we have high dynamics, we have rotary tools, we have rotary workpieces. So you need to have certain technologies in order to capture those high dynamics, like piezo technology. Of course, automated evaluation and more AI coming into the picture, but still the evaluation part has to have certain intelligence, right? Not like what we are doing in R&D, that we are gathering a lot of information and try to analyze it. Here in production, it has to go automated. And also, of course, the system should not interfere with manufacturing execution, right? Both hardware and software. Often specific integrated measurement technology is required. So you use maybe the same sensor types, but how you're using, where you're placing can be specific from machine to machine and application to application. We are talking a lot about monitoring. The sensor input is used, but for really what? When it comes to monitoring, we have this. We are using cutting tools, we are using abrasives, and there is a very clear correlation between the wear state of those abrasives and tools with the part quality, right? And that's why that the monitoring of tool wear is important, and that we do with certain signals. We are monitoring machine and process abnormalities because the tool can be still new, but certain things can behave differently, like the pump maybe of your coolant tank is not working, and then suddenly you don't get the coolant, and it will affect your temperature and maybe your product at the end of the day. So you need to capture that. We are using sensors to monitor the status of the operations. We would like to see the number of parts, scrap rates, delivery time, so that we can see where we are when it comes to the plant manufacturing. One very important reason is also to decrease the operator to machine ratio. That is very important because we do not want to have one operator standing by the one machine. We would like to have maybe one operator managing 10, 15 machines, right? And operator or head count, let us say in lean manufacturing terms, it's a big cost of the total manufacturing. So we would like to decrease this, and that's why we need to be able to monitor your process. One big topic is also when you monitor your process and machine is you are kind of making indirect quality measurements, especially if you can correlate certain signals that you are measuring in the machine and the quality parameters that belongs to that part after machining. If you can find that correlation, this means that you can use this as a safeguard in the machine, those signals. If they are within some certain limits, you know that the product will be okay. Then you don't need to make a lot of measurement, right? And quality measurement is, of course, a big cost. Process optimization, yes, we use sensors to make process optimization. Yeah, either we connect the signal back into the machine, like we are doing at Kistler as well with certain customers, and then the machine does certain things depending on the signal levels. This is one way. The other way is that you collect a lot of data and then you need to analyze in order to improve your process or machine. Traceability, yes, especially in aerospace, as you know, that you would like to really make sure that that you have a history, a trace of the manufacturing part. So really, why we are using sensor? Yes, to monitor, to make inequality measurement, process optimization, traceability. And that is really important if you are planning to use a sensor. It has to be at least one of those reasons that you are using, and a little bit upper level is really the KPIs that we are chasing, right, in production. Let's jump into now to some cases that we can at least share with you. And before I start with that, I will talk again about why do we measure, what do we really measure? This is a very typical force measurement. From turning, we have three forces: cutting force, feed force, passive force. You can see quite a lot of things with the force measurement, things that you don't see with vibration measurements. This is one of the reasons we are really focusing on to capture the force. Of course, vibrations are also important, especially with the tool breakages. But you can see certain things in the force. You have static part of the forces, you have dynamic part of the forces, but you also have the ratios, and that is friction. Like in grinding, we are looking to the normal force and exit force, right? And the ratios between. The force signal consists following information. It tells you about chip formation, tool wear, tool breakage is also included, of course, here. Surface quality, as I said, you can see certain correlations between the force signal and the quality parameters, like how straight you are cutting and turning, like the surface, depending roughness, depending on the dynamic part of your signal in milling. So there are certain correlations. Imbalance of the spindle workpiece system, you will have more dynamic part, more noise, so to say, if you have some sort of run out in your spindle or your part is too round. Interrupted cuts, yeah, that can affect your part because maybe you have some impurities in your material. Out of roundness of the workpiece, as I said, yeah. So if you start turning and then your signal is quite noisy, then maybe if it is outside of certain limits, you can already say that I will not machine this part because I know that the roundness is not good and it will not be good at the end of the day because you don't have enough allowances. Then you can sort out that instead of machining and losing time and cost. Microstructural effect, as I said, hard and soft parts. It affects the force signal. Machine mechanical electrical configuration, yes, machine stiffness is a stiff machine. both dynamic and static, it will affect your force values. External forces, it can come from coolant, oscillation of certain equipments, they will affect the signal. So really, there are certain things that you see with the force signal that you don't see with the vibration measurements. That's one of the big reasons that we are really focusing on the force measurement, direct or indirect. Let's now jump into certain examples. I will talk about lathe, where we are using force shunt, so like indirect force measurement. We have Swiss type machines also in our production. I will show how we are doing that. We have hard turning machines, sensors integrated in the machine structure, even in the Capto tool holder. Then we have some milling machines also, and that I will show some examples on. Let's start with the lathe. As you can see, this is and just a schematical view of a machine with the cutting tool in an insert, represented with this yellow triangle here. You have a tool holder, the gray, dark gray, and then that is located in the machine tool holder housing. And then you have some machine parts, which is moving, of course, back and forward with a certain axis. So you have some constructions. Now, the task is really being able to install the sensor at certain positions so that you are as close as possible to the cutting point, but still not interfering with the manufacturing execution and movements and so on, and to capture the tool wear. In this case, we have cutting forces. We know that the forces will cause deformation. It will cause certain elastic deformation and movements of this tool holder in the housing, and then that deformation will go through the whole structure. So what we have done is that we have installed one directional piezo strain sensor, which is measuring the deformation, the strain in this direction. So it's in the housing. And then we have installed another one far from the cutting tool. In this case, that is measuring in the transverse direction, the strain, but still piezo sensors. And then, in the reality, it may look like this. And of course, that is something that we are also, at certain cases, putting even on the tool holder, as you can see here. We are partnering with the tool holder supplier and tool manufacturer, Horn in this case. So we have a patent pending, but the idea is really placing the suitable sensors at certain positions if you are really chasing accuracy, or at other positions if certain levels are enough for you. This is our know-how, of course, right? But if you look to the signals, you can see that now we see this relative change, as I mentioned from the beginning. We have a Neve tool giving certain signal. We have a Warn tool giving another signals, as you can see. Then you can really see the difference and put the levels, of course, what is normal, what is not, and then the machine will be stopped by our measurement technology, which is connected to the machine. Far away from the tool edge, we still have, you can see that, good enough levels of the signal, and that is, of course, thanks to the piezo technology and how we are building our sensors, of course, around that. You can really see the difference between a Neve tool and Warn tool. So really, with Kistler know-how, where to place what kind of sensors, you can really capture with much more flexible and cost-effective way. Another example is now Swiss type machines. In this application, we are talking about turning of 10-volt components. So it's really important that to keep the forces within certain limits. Otherwise, high forces on this 10-volt components, they increase deformation, and at the end, the part is outside the tolerance. So it may look like this. As a start, we have our dynamometers inside the machine. We have the tools on top of it. As you can see, the part is a membrane. You can see here. And then if you look to the forces, we have 3 cutting forces. You can see here. And this is the first part. how the forces look like, and then after 100 parts you are really reaching certain limits, and that level after that level you are deforming your material. So we know, so even if the tool is not too worn, we know that that level should not be overshooted, right? So we should not pass that level. So, and then in the second step, of course, then we can build in our sensors. You can see our 4 sensors here in the construction, how it looks like in the reality, and then you have the tool holders located here in the below part. But this is also a way that to integrate the 4 sensors, yeah, inside the construction. And yeah, so as I said, flexible and cost-effective and simpler way. If you look to now hard turning machines, now we are talking about vertical machines. As you can see, we are cooperating here with the hard turning machine supplier Miganti. In this case, you can see the machines here. The cutting tools are here with the inserts. With the, yeah, you have 4 cutting tools. You have a big part that you are machining, and yeah, and then we can place certain sensors. Again, the piezo strain sensors in the housing. We have 4 sensors in the housing. We have piezo strain sensor also inside this construction here that we are using now. So we have different strategies depending what we are looking at. Yeah, so if you look to the force signal, as I said, there are certain things that you can see. For instance, small edge chipping, which will cause, you know, force increase and decreases, right? And this is something that we can really capture with this signals, simple and one axis sensors that we are integrating into the construction. So now it's a standard in Miganti machines in turning. So we are utilizing this piezo strain surface sensor that we are putting it inside the machine. And in order to have a redundancy, we also have piezo, again, vibration sensor that we are using, and then they are connected directly to our industrial charge amplifier, right? One is a little bit more force measurement, as I said, is a piezo strain sensor, so it's really measuring the force in an indirect way, since you are measuring the deformation on the surface, and then at the same time vibration. So what we can do with our software and electronics included in this box, that we can use either the signal as it is, or we can really make some filtering. So we are really looking only the dynamic part of the signal, because then it will be easy to capture only the breakages. But if you would like to go for wear and other stuff, quality parameters connected to, then you would like to use the quasi-static signal instead, so the force measurement. But we have this flexibility, and if you want to really go for even high dynamics, then you can also use the vibration sensor. Yeah. So in this case, in these machines now, we have these 2 we are utilizing for tool breakage detection, tool wear detection, and also as a crash safety, right? So sometimes the wrong programs are loaded, or operators are using or making some errors, and then we do not want to machine to crash into other machine parts, or to the workpiece, destroy the machine itself or the part. So by using this exactly the same system, the machine will stop directly when it realizes that there is a small crash, right, or touch. So this is a standard solution now in Miganti machines. Now we are moving into the milling machines instead, so leaving the turning, but we are using exactly the same strategy. We have, in this case, together with our machine builder, that we are cooperating with Lagoon Machine Tools, for instance. In this setup, we are just demonstrating that we can even use our stationary dynamometers that is being used for research. You can see that it's integrated in the machine spindle on the backside, as you can see, but it can also be installed on the below our workpiece, and then we are using exactly the same sensor type, again a piezo strain sensor that we are putting in certain positions with Kistler know-how, in order to detect small tool cutting forces that is happening in the milling operation. So we are making again an indirect measurement of the cutting forces, and we can calibrate or verify with those dynamometers. So let's look to the signal again. Now we are measuring the deformation in this position, and we have placed the sensor there because it's our know-how. And if you look to the forces here, then you can see that we have cutting forces that are being measured with the 9255. So you are making milling operation. You have cutting forces, and you can see that there are certain even small steps. And then if you look to the upper plot, where we can see is the deformation on the surface of the spindle construction. So even if they are very, very small, we are talking about, these small steps, 5 to 10 Newton, we are still capturing this deformation. As you can see, they are really resembling those signals. Yeah. So even if the forces are small, if the machine construction is stiff enough due to the moment which is causing bending of the deformation on the structure, you can really capture that with our piezo strain sensors. So to make some sort of summary, we are utilizing our sensors, which we have had many years experience already in many other applications, and many of our customers, especially machine builders, have been utilizing this. Those sensors, they are again piezo strain sensors, and then we have also force sensors that we can also integrate in the machines or even in the tools. These two sensors, 9241, 9243, one is measuring in the transverse direction in this direction, and one is measuring in the longitudinal direction in this direction, and they can be embedded or integrated in your tools and machines, right? And then we have our surface sensors, surface piezo strain sensors, these three, and then they are rather also easy to install on the certain positions and places, and found the forces. So we are measuring still the forces, but in an indirect way. So we have those flexible and simple yet piezo strains and force sensors. We are then able to have either standalone systems, but still with machine connectivity, or you can directly connect to your machine, as many machine builders utilizing our sensors do. If you want to have standalone systems, we have Maximus family, Maximus BL and Maximus TL, where they can also be connected to the machine, right? So you have a system which will give you alarm, but it can also stop the machine. And then on the screen, you will be easily see the correlation between your new tool and worn tool, thanks to the signals that we are collecting with our flexible and cost-effective sensor systems. Then we have our cooperative parts, but also our business partners like Migante, as I said, we have industrial amplifiers with certain filter settings and so on that we utilize, and then we either analog or digital or with IO-Link that we are connecting directly to the machine, to the PLC or to the NC, and then tool breakage detection, especially at Siemens control system, we are now starting to offer more and more. So if you are interested in, please feel free to contact your local colleagues at Kistler. Then we will supply you the programs together with the right sensor technology and electronics, so that you can make tool breakage detection and machine safety, especially at Siemens. As I said, we can offer this. So as I said, either standalone system with machine connectivity, or the signal into the machine to start doing directly tool breakage detection, but also in the near future, we will also offer intelligent machining. So we will build control loops, and that will be also standard package from us the coming year. So this is basically very, very condensed way what we are offering when it comes to machining monitoring. Simple, cost effective, with a lot of Kistler know-how in the background. Good. So now I will make some summary. As I said, we have flexible sensor integration systems with Kistler know-how and experience, and they have been in the market many years in other applications, and machine builders have been also using them in the machining, but now we are offering even the know-how in the background and as complete packages. We are still relying on piezo force sensors. When I say force, I am also meaning that the piezo strain sensor, because they are measuring the force, because we are really able to capture even small high dynamic cutting forces. And in some cases, we are filtering away directly the drift if you have long cutting times, but it really depends on the technology and places that you will be using, is where we have also the Kistler know-how. So you can use the same solution for tool wear and breakage monitoring, indirect product quality control, since it's correlated to the tool wear and final quality. Traceability, of course, Maximus, it can also, it has this memory, it can also be connected to your shop floor LAN, so you can also save the data. And machine condition monitoring and protection is also why our customers utilizing machining monitoring, those two solutions, so that they are even active when you are not machining, right? So that if the signals hit certain limits, you stop the machine so that you don't crash and cause too much damage in your machine. So it's very important that we are covering this. So this means that we are really becoming a solution provider in machining monitoring by utilizing our know-how and our existing products already. We are working with the leading companies in the tooling, as I said, given some names like Horn from Germany. We have Lagoon Machine Tools. We have Miganti, and we have some others that have been utilizing our systems. Also like grinding machine supplier Juvalit Köping from Sweden is also a partner for us. And of course, we are supporting you not only with a wide range of piezo-based solutions, but also with deep knowledge on machining applications and machines, right? And this is also the strength in our organizations in the group, that we are able to utilize that already existing knowledge together with our know-how in order to make more cost-effective and really flexible solutions in machining monitoring. By this, I would like to end my presentation. The record will be shared with you, as I said, and yeah, David, maybe you can help me to open the Q&A session if we have some questions. Thank you.
Sure. Yep, thank you, Bulent. That was very informative and an interesting topic. I appreciate you sharing that with us. I'll remind everyone, if they want to use the chat feature on the right-hand side, go ahead and ask your questions there. And I appreciate too that you handled one of the main questions that we typically get is about the system, if it can integrate into the machine directly, or if you needed an operator at the machine. So I like that you went over the Maximo solutions and the signal conditioners that we use to integrate back into the machines. So that's a pretty common question that we get. Something else that I was wondering, if you wouldn't mind, it sounded like you touched on it a little at the end there, but you know, with the Kistler know-how, does Kistler offer any assistance with placing the sensors, interpreting the signals, trying to understand their machining process, or is that kind of left up to the customer on their own?
I think we are. We can say that we are offering this when it comes to discussing and finding the right position, the right sensor, and so on. That is the way we have been working in many cases. So we can say that as a short answer, that yes, we are offering that. Yeah.
Okay. Great. Yeah, we certainly like to partner with the customers and work with you as a solution provider and make sure that we are working together instead of just providing the sensors and leaving you on your own. Are there any questions? I'm not seeing anything else in the
I
chat here.
I see one.
Okay.
Yeah, I see one. What distinguish Kistler monitoring solution over other available solutions in the market for years? Yeah. I can say directly that one thing is the cost effectiveness part, because as I mentioned before, that we are really utilizing single access yet piezo technology based sensor system together with our one of our solutions, you know, and know-how, and of course this which is and can be integrated in a very simple way and in many other many machines, especially if you're talking about Maximus. So cost effectiveness is one, flexibility is another one. As I said, we are flexible when it comes to using certain sensors and placing them also as a retrofit in the machine. You don't need to make big changes in the machine, and you don't need to have certain software or Siemens version or Fanuc version and so on. You don't need to that in this case. So cost effectiveness, flexibility, and also the simplicity is the other key parameter, because really with a touch screen, in this case, you put the levels and then it communicates with the machine, say it tells you if it's okay or not, for instance. Yeah. So I think this three parts. If I can also add as the piezo the reliability, because thanks to the piezo, we are really capturing all high dynamics happening in the process, and of course with an organization and know how we can also calibrate and make a service of the monitoring system, right? So we are keeping it reliable. So cost effectiveness, flexibility, simplicity, and reliability. I think that these four parts make us better than many other solutions existing in the market.
Thanks, Blunt. I'm seeing a few great questions coming through here on the chat now. So we'll start off with a question from Patrick. How does the Kistler system deal with the storage of the sensor data?
Yeah, so it really depends which one of those we are looking at now. If it is the Maximus, of course, we have our memory and yeah, and local, but also this can also be connected to the shop floor LAN. So this means that you can also use your server space to save the data. When it comes to the lower part, the same thing goes here. If you are connected to your shop floor LAN, then you can also upload the measurement directly to the cloud system or into the machine.
Great.
Yeah.
I got another a great question here. How do you compensate for thermal drift when embedding your sensors into the machine? It's always the problem, right? Thermals.
Yeah, exactly. So you can do this in different ways, but of course, we should also be humble here and say that if you are, and if you really feel that you must be very close to a cutting point where you have a lot of temperature change and you cannot really conceal your sensor, and then you are making maybe hours of measurement, and you really must measure the force absolute values, then we can say that maybe the piezo is not the right strategy for you. That is absolutely the case, right? But until now, in many cases, we have succeeded to either get rid of or decrease the amount of the drift by placing the sensor at certain positions where the thermal or temperature effect is minimized. This is one strategy. The other strategy, that if you are interested in tool breakages, then you don't need really the static part of the measurement. So this means that it's enough to work with the high dynamic part of your measurement, and this is what we are utilizing when it comes to especially tool breakages, as you can see in this figure here. That when you make certain filtering, especially high pass filtering, then you get rid of your drift. So when the signal is connected to the machine or to our Maximus levels, Maximus product, then you are only looking to the dynamic part of the measurement. So this means that then you don't need to consider the drift. So it really depends, but as I said, in many cases we have succeeded it, but as I said, we need to be also the humble. There are also certain cases where piezo may not be the right strategy for you.
Absolutely. Thanks, Bullet. And we have another question here. Assuming that the sensor, like the 9232A, is connected directly to a Siemens NCU, how do you achieve high-speed evaluation and high sample rates?
Yeah. So this really happens, yeah, in the case that like now we are talking about Miganti that we are working on now, and of course, if you look to the speed of the NC and PLC, we are talking about, let us say, a little bit less than maybe 1 millisecond, let us say, a half millisecond in the PLC that we are actually this week that we are making the acceptance testing. And of course, then it limits. Maybe you can go up to certain, you can measure up to maybe 1 kilohertz, yeah. But for certain applications, that is good enough to capture still the tool wear. For instance, in turning application, right? But maybe this will not be the best case if you're talking about high-speed milling, right? That's also correct. So it really depends what kind of operation and what you are up to. There are certain cases like apparently we are doing with Miganti and in Siemens by utilizing our 5074 and 9232, and that is absolutely good enough, more than enough to capture the tool breakage and tool wear still. But high-speed milling, maybe not the best case, right? You will for sure see still the tool breakage, but maybe you will not be able to capture right away, but you will lose some some milliseconds before you capture that. But my experience from machining, if you break the tool, you will see it anyhow in the and the Siemens NCU will not be the bottleneck. It will not be.
Okay, just one more popped in. I'm curious if the machine tool builders have experienced issues with loss of stiffness in the machine by integrating these sensors into joints and tool holders as we have seen today.
No, because I can, but again, it also depends how you're doing, right? I mean, of course, if you are integrating in a way that the whole machine construction is being changed, then it will be a stiffness change, of course, both dynamic and static. But if you are talking about the solutions that we are discussing here, mainly our one-axis piezo strain sensors, it is not affecting, no, because of course you are making a small holes, but this change not in the static stiffness but dynamic stiffness part is, as far as we have measured, is negligible and it will not affect you. But of course it depends on what you are where you are adding that signal, right? And that is our know-how coming to the picture, of course.
Right. Yeah. I'd like to add that, we certainly want to give you an honest assessment of your situation, your application. We're not out to try and just sell you a solution. We want to be a partner. And if it works for you, great. But if it's not a good fit for you or not a good solution, then we're happy to recommend alternatives as well, even if they don't come from Kistler.
Yeah, I see one more question. Is
Okay.
it possible to integrate third-party developed software to your Maximus system? I don't think so. Maximus comes along with the hardware software as a package, so that cannot be done. But of course, yeah, if you would like to analyze later on the data, then you can export and use.
Correct.
And high sample rates, yes, sample rates. It depends what kind of electronics you are using. The only limitation of Maximus system is that we have 8,000 measurement points. So Maximus, as of today, it's limited to small, short cycle machining if you would like to use a high sampling rate, right? But as I said, in turning applications, again, we are mostly interested in when it comes to the tool breakage and tool wear. As you can see in the pictures here, you are mostly interested in the static part of the forces. But again, depending on what you're talking about, milling application, important to stop the machine, high-speed milling, and so on. Of course, then Maximus will not be the best choice for you. Absolutely no, right?
Okay.
Let's see. Okay. I'm curious if the machine tool builders have experienced issues with. Okay, you have. I have answered this. Yeah. I think we have gone through the questions.
I think we have. I'm just adding my email here. If anyone has any additional questions or would like to discuss their specific applications further, please feel free. I think we've hit the time here. So let me just david.allen@kistler.com.
Correct.
Oh, looks like it cut off my my response there. I apologize for that. But yes, if you have any additional questions or would like to discuss your application any further, we're happy to help out. Bullen and I, we're happy to schedule a meeting or whatever you need to do to help with your application.
Okay.
All right. Thank you all so much for attending, and we look forward to talking to you again in the future.
Thank you. Thanks a lot for everyone. Yeah. And thanks, David, also supporting me today. And yeah, we can reconnect, I think. Yeah. Okay. Thank you. Bye-bye.
Bye.